Today we are going to do section 3 on page 262, but before we start, it is the integration by parts, which requires you to do both differentiation and integration at the same time, which being that those two are reverse operations, that can get confusing. So it's helpful if you get yourself this thing as part of your cheat sheet. This is on page 489 of the derivative formulas in the book Calculus 1. Okay, we are now in Calculus 2, but this is in Calculus 1. So let's go over this quickly to refresh your memory. The derivative of xn, of course, is nxn plus n minus 1. And then the integral then is, you do the opposite. You raise the x by 1, the power of x by 1, divide by that power. That's how you do integration. Similarly, the derivative of natural log is 1 over x. And then, of course, the integral of 1 over x then is natural log. And so on. Derivative of e is just e. Okay, derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent is secant squared, derivative of cosecant is negative cosecant cotangent, derivative of secant is secant tangent, and derivative of cotangent is negative cosecant squared. So keep this page next to you if necessary, which might help you in keeping track of what are we doing. You know, sometimes you will refer to the integration side and sometimes refer to the differentiation side. See, it's side by side and good for keeping the brain clear and not get confused by details. So having said that, we are ready to do integration by parts. This is on section 3.1 of page 262. The integration by parts is developed by a very simple formula, the product rule. Now the product rule, of course, says that if you have h of x equal to two functions multiplied together, f of x times g of x, then h prime of x by the product rule equals to f prime, okay, g plus g prime f. Okay, and I'm just skipping some of the x's because there are too many x's to write. And then if you integrate everything, then it will become this thing right here. That it will everything in here. Then you get h back, which h is f times g, but when you integrate, this side then becomes integral of f prime g plus the integral of g prime f. Now again, I'm skipping some of the dx and stuff, but that's printed in your book, so you can follow along easily. Now in that case, we are going to isolate one of these things. We're going to isolate f prime. What are we isolating? F times g prime. So let's put this on by itself. Okay, so then we have f times g prime, integral of f g prime. It will equal to, move that to the other side of the equation, fg minus integral of gf prime. All right, I'm skipping all the dx's and stuff for now. And then, so far so good. And then what we're gonna do is let u equal to f of x, and then v equals to g of x. And what that means is that, of course, that du equals to f prime of x dx, and then same thing as dv. dv equals to g prime of x dx. And then when we plug all the stuff back in here, then we have this thing becomes the integral of u. Okay, g prime is this thing, which is dv, equals to f times g, which is u times v, minus integral of g times f. Well, g is v, and f prime is du, so that all works out. Now, having said that, I haven't really done very much. It's like, well, what about it? So what? This formula is called integration by parts. And what you do is you start out with some integral that's in this form, that somehow you can identify it as a function, and then the derivative, the differential of another function, and then you will then follow this formula, and so that it becomes some kind of multiplication of the two functions by you have to integrate v to get dv to get v back, and then you write down this new integral. And this looks like, and what good is that? Because the formula gives you another integral, and you are trying to integrate, right? So you end up with a new integral, and that doesn't seem to be very helpful. Well, it's not necessarily helpful, but it can be if this integral turns out to be easier to do than that one. Okay, if that one's very hard or impossible to do, and this one turns out to be a piece of cake, then you got a mate. So that's the hope, and that's the purpose of integration by parts. So having said that, let's look at an example. Okay, the first example, which is example 3.1, we will do it here. Integration example 3.1, and then which says that we are supposed to evaluate x sine of x. Sine x dx. Now this integral cannot be done by substitution. Okay, to do substitution, there's an extra x here, because you can do substitution if, say, this x instead of x is x squared, because if it's x squared, then by the chain rule, the derivative of x squared will become 2x, so then you will have an x here, and then you're okay. But that is not the case. So the substitution is out of the question. So how are we going to do this? Well, we're going to use this brand new trick that we learned called integration by parts. And we will, the integration by parts, the trick, the most important part of the trick is figure out what to pick for u and what to pick for v. So in this case, we are going to choose, as your book suggests, we'll choose u equals to, we'll pick u equals to just x, and then v dv equals to sine x dx. Let's see. Okay, we're not going to write it this way. If u equals to x, and then we figure out what is du. Well, du is then dx. Okay, just work the differential like you always do. Take the derivative of x, and then we will put dv. So you take care of just this part. dv will take care of this whole thing, sine x dx. Okay, the whole thing. So then what is v then? If you integrate this part. That's what I mean by you have to do the differentiation and integration in the same problem. So here you do differentiation. That happens to be an easy one. Here you have to do integration. What is v if dv is sine x dx? Well, then you remember what becomes sine from that chart that I just showed you, and then maybe even look it up, and then you remember that it is cosine. The derivative of cosine becomes sine, except that there's a negative sign, right? So v equals cosine x, but the cosine x, when you take the derivative, is a negative sign. So we have a negative sign to worry about. So if we stick an extra negative sign here, take the derivative of cosine, it becomes minus sign, cancel out that negative sign, so it becomes the positive sine x. So that's what v is. Now we'll follow the formula. Then now we got all the things set up. What does the formula say? The formula says you need, if you have u dv, which is what this is, u is x, dv is this stuff in the end, so it's all set up. Then it equals to u times v. So u is x, v is negative cosine x. So we're going to multiply those two together. So it's the first uv becomes x, negative x cosine x, uv minus, the next part of the formula says minus v integral of v du. So we are going to do that. Integral of v, what's v again? Is minus cosine x. And du is just dx. Okay, let's not mix that up here. All right, so now we have a much better situation. There's two negative signs here. So let's make it positive. And then what do we have now? Well, this part is okay, right? And what about this part? This part is turns out to be much easier than this, because this one we don't know how to integrate, thanks to that x here, and this one not having a square or something that helps us out. But this one is a simple integration. What's the integral of cosine? Well, look at your chart. Then the integral cosine is just sine x, right? So then we are good. So then the entire answer is that thing plus that thing, and then being that it's the indefinite integral, you have to add that constant, which is c. And then we can look at, what did the book do? Minus cosine x plus sine x plus c. We got it right, see? And it's a look at how quick and easy that is. So this is where the integration by parts formula shines. Is a quick and easy way to handle something that's basically impossible before. Okay, and so that's what you're gonna do in this entire section, is continue to do this. The trick, however, is to find out what do we set up for u and what do we set up for v. Sometimes it's hard to tell. Then you have to try each. Like, why we set up u as x here, why didn't we set it up as sine x? Well, the reason we do it this way is because this way works. Okay, if you set it up as sine x, you might get into a mess. I don't know. Or maybe it works, who knows? But the point is, this works, so we'll stick with it. Okay, and next, let's look at the next problem. But before that, we are at page 264, and let's look at something your book come up with that's kind of cute. It's called, at the top of page 264, the book gives you a hint of how to do this. So what should you pick for you? That's the hardest, most confusing part of pulling this trick, the integration by parts. The trick is that you need to follow the law that's called, where is it? Liat. L-I-A-T-E for integration by parts. And what does that mean? At the top of the page, it reads out to you. L is logarithm, inverse trigonometric functions, algebraic functions, trigonometric functions, and lastly, exponential functions, which is that's somewhat funny, but that's the rule. Okay, you remember, I stands for inverse trigonometric functions. In other words, I stands for IT. Okay, which is not used that much, but you need algebraic functions just means any old thing like x squared, yeah, something like that. And then T is trigonometric functions, sine, cosine, etc. And E, of course, exponential functions. Notice the logarithmic functions stand first. So once you write that thing down, and when you do your homework, write that down, and then write this thing down, then you're good to go. Anyway, so so let's look at the next example. Now, example 3.2 on this page, the integral of natural log of x over x cubed dx. Now, again, when you just look at this, you can't do substitution, because to have substitution, you need to the chain rule has to come up with x to the power 3. Or something. In fact, it has to come out with 1 over x to the power 3. And off the top of my head, I wouldn't know how to do that. But so we're going to try integration by parts, see if that works out a little better. The u, being that there's a natural log of x, we follow the rule, which says that u has, the first choice for u is the natural log. So we'll choose u equals to natural log of x, which means du equals to 1 over x dx. And then v is the rest of it. So we'll let dv equals to integral, sorry, there's no integral here. We're talking about the differentials. Okay, dv is just the rest of it. What's left is dx over x to the power 3. Okay, and then now we need to do the integral using the power rule from the chart I showed you. We will have v then equals to, this is x to the power negative 3 raised 1 becomes x to the power minus 2, and divided by that power. Okay, yeah, that's about it. Okay, that's the integration part. So now that we did that, and now we're going to follow the formula and see if it leads us to some place good. So that equals to u times v, which is that times that. Let's write that down. Natural log of x times x to the power minus 2 over 2 over minus 2. Yeah, don't forget the minuses. uv minus v du, right? That's what it says right here. Or you can refer to the book, your book formula. Anyway, we need to integrate v du, which is x minus 2 over 2, negative 2. And then du is 1 over x dx. Right? That's du. So that's v du, following the formula exactly and carefully. Okay, and not missing any negative signs. So that's pretty good. So let's get rid of the negative signs to make it slightly less confusing. And so this part is good. Now we just need to see if we can get this thing to come out. And this thing is very nice because, as you can see, what is it? It is that's minus 2 and then minus 1 more. So this part, just this part, okay, equals to the integral of x to the power minus 3 and then divided by 2, right? And what is that? And that you can use the power rule, okay, to integrate this thing is raise the power by 1, divide by that power, which is equal to, so x raised to the power by 1 becomes minus 2, divided by minus 2 times 2 is minus 4, and that's about it, okay? And then, so what do we have? So we have this thing plus that thing, okay? And let's double check. It has, so the answer is minus 2x squared on the bottom, as your book shows, times natural log, and then minus right here, okay, minus 1 over 4x squared, which is that. And then, of course, we don't forget to do the plus c for the indefinite integral, which is what that is. And so then that's it. That's the end of the answer. Now, for you to present your answer, you should probably rewrite this out instead of just do that. But for me, I like to save time, and therefore, this is all I'm going to do. Now, let me remind you that whenever I do an example from the book in class, it's very important for you to redo them when you're done watching the video. That way, you can solidify your grasp of the material. I know a lot of people think, well, I already seen you do it, I know how, but not necessarily. I mean, if you really think you know how, let's see you whip it out real quick, right? Shouldn't take long, being that you already know how. The way you redo a problem is you simply look at the problem, right? And such as, say, this one, but cover up the solution. So you only write down the problem, then you put the book away and try to do it from that point on, from memory, from deduction, I don't care. Just you need to redo it. And the benefit of doing that is that if you do get stuck and, oh no, I forgot how to do this already, then the book is right there to explain it. And of course, in my video, I already explained it and you can refer back to it. That's how people get good at calculus. Okay, and well, good at math in general. And that's a very important skill that should be done from calculus onward. Like any more advanced math you do, you absolutely want to repeat what the professor says. That is, reproof everything, redo all the examples, and then you got a good, strong grasp of what's going on. So please do. So please repeat the examples I've already gone through. And then the next example 3.3, is the same thing. You have to apply integration by parts. The difference, however, is that once you go through the first round of integration, the thing looks slightly better, but still not good enough. You can't integrate it right away. So you apply the integration by parts again on that part of the thing. Like, what I mean is like, say this, okay? You start out look at this thing. You start out with x squared, etc., which you can't integrate right away. So you plug in the integration by parts and come up with something. Now you knock the power of x down to just 1. Okay, it started with x squared. Now you're down to x. But that's still not good enough. You still can't do it. So you repeat the process and do integration by parts on just this thing right here, right? And when you do that, then you knock that x power again. Knock it down again, and then you'll be able to handle it. So please do example 3.3 as part of your homework. The homework that sometimes are assigned just from examples themselves, they are very good for practice because those are the ones that I feel that you can handle. But so instead of watching me do it, it's better that you do it yourself, which is a much better use of your time. Next, let's look at example 3.4, which is the integral of t cubed e to the power t squared dt. Now, if you're wondering, why is it t now, not x? We don't care, okay? It's just these things are called dummies or something. It just, they all work as t, x. What's the difference? We'll do it the same. And so, a rose by another name is just as sweet. So the problem with this thing is that you can't follow the rule, the Liat rule, L-I-A-T-E, directly. The reason is because you notice that e is to the power t squared, not just t, which means that when you take the derivative of this thing, it will it will have a t attached to it. So u doesn't need to be t to the power 3. You can just let u equal to t to the power t squared, okay? Because this part, when you take the derivative, will take care of the rest of it. And let me show you what I mean by in a second. So if we let u equal to t squared instead of t cubed, which would land you in hot water actually, because the Liat rule doesn't always work. So you have to sometimes be flexible. So if we let u equal to t squared, then du is equal to 2t dt. And then on the other hand, we'll let v equals to the rest of it. Okay, where's v? And so v has to be equal to what's left, which is t. There's one t left, e to the power t squared dt. So then, what is that? Oh, sorry, it's dv. Let me write down the d here. Okay, dv is that. Now we need to do the integration. So then v equals to integrate. Let's look at that chart before. But for e, you remember, okay? Derivative of e is just e. The integral of e is also e. So then that's just e, which is fine. E to the t squared. But we have to take care of something. And now if you were to take the derivative of this thing, it will become this thing itself times the derivative of what's up here, which is 2t, okay? But this has only one t here, so we'll divide it out. Let's get rid of and now the derivative of this whole thing will become that. See? And so, yeah, if you try it, then you see that it works out nicely. So now we got all the parts together, and we follow the formula. And what's the formula? The formula says the integration by parts means we'll take v, okay, u times v, u is t squared. V is that thing, e to the power t squared over 2 minus v du. So minus I'll write it a little bit lower because I'm running out of space. V, which is et squared over 2. Du is this stuff, okay? So du is 2t dt. Well, yeah, I guess it didn't work out the way I imagined, but I thought that if we keep some of it here, well, actually, we need some of it here because to do the integration, I guess. But anyway, it's going to work out, okay? In this case, we're going to luck out. And so the 2's cancel here. And then so this is integrating this thing, we get that works out nicely, okay, using substitution. So that would be equal to e to the t squared because the derivative of e is e. But you have to watch out for some numbers. So then if you take the derivative of this thing, that will become e to the t squared, but it will also have a 2t in it, right? which is what we just did. So to take care of the 2t, I mean the 2-bit, the t is here, but what about the 2? We'll divide it by 2 to take care of it. Or you can do this by use substitution. That's fine too. But being that this is a short problem, we're just doing use substitution in our heads, basically. So you just come up with something that will quickly take the derivative into that. And that should be it. Okay, let's add the constant. And the answer should be that thing, which is 1/2 t squared e to the power t squared, minus, here's the minus sign, and then this thing, which is 1/2 e to the power t squared, plus c. See, I got it right. Next, let's look at example 3.5, where you evaluate the sine of the natural log of x. Now, how would you do that? Well, you let u equal the sine of the natural log of x, but then you end up with some weird thing that you end up with cosine of natural log of x. And what do? Well, you do it again. Okay, you do this. You pull the same stunt on the cosine one. That is, and then you end up with sine again. See, look at what your book shows. First, at the top, so you see, when you do all that stuff, you end up with the integral of cosine natural log of x. So when you pull it again, you end up with the sine of natural log of x again. So you go back where you started. However, the way it works out is that that's going to help you calculate the result, because you have an extra one on the other side in such a way that you can add them up and subtract and all that stuff. So I'll let you decipher the details. Okay, it just, well, that's just the you're close to the end of the answer. So the mystery, I'll let you figure out the rest of the mystery, which is example 3.5. Okay, please do example 3.5 as part of your homework. Next, let's look at example 3.6, where you are supposed to evaluate the integral, which what do? Well, you plug in the numbers and evaluate it. In this case, you are doing the integral from calculating the area under the curve from 0 to 1 of tangent inverse of x. The tangent inverse is not in the chart, so please look up how to take the derivative of tangent inverse. It equals to 1 over x squared plus 1. But once you know that, then everything falls out pretty quickly. And then you plug in the evaluation numbers to come up with whatever the result might be. So please do example 3.6. With that, we have come to the end of the chapter, the section. We are going to skip the last example where the book wants you to do the volume of revolution, which I don't know why we're doing that right now. We're doing integration by parts. So let's focus on one thing at a time and get it down. Okay, so to be good at integration by parts, please do the following examples, following problems, homework problems in your book. And please notice that all the homework problems I choose very, very carefully. I pick the least amount of work you have to do to become proficient in the subject matter. So please do all the problems carefully. And when you're done, I will be talking about them in the video. And the problems I want you to do, which is also posted under this video in the video description, is problems 7, 9, 11, 13, 15, 19, 23, 25, 26, 27, 47, 53, 55, 57, 63, and 65. And notice that problem 63 is unusually difficult, I think. So I posted a hint below. So if you have trouble with it, look at the hint. Okay. So that's that. So please go do your homework, and when you come back, we will talk about the homework. Now that you're done with the homework, let's talk about it. Problem number 7, where you have to integrate the natural log of x dx. Now, the formula of the natural integration of natural log is already given in chapter 1, but we're going to redo it here just to test to see if the integration by parts method really works. So what we're going to do is, I have it written, I did it in my notebook. We'll let u equal the natural log of x, following the rule on top that says, see the corner there, LIATE, the Liat rule, right? L stands for natural log, so you will choose that to be u equals, so u will be chosen as a natural log of x. Then du is taking the derivative, becomes 1 over x dx, and then dv is what's left. What's left is just dx, so then when you integrate that, v is just x. Then you follow the principle, and then the answer pops out in one line, and nice and neat, and that is correct too. Okay, so that's problem 7. Next, problem 9, we're integrating tangent inverse. Isn't that already done in the example? We'll just do it again. Okay, to integrate tangent inverse, of course, the inverse tangent, the inverse trigonometric function is the second one. See, in the LIATE rule, Liat. So the inverse tangent, so you choose that as your u, and then take the derivative of tangent inverse, which is 1 over 1 plus x squared. Okay, if you don't remember that, just look up some chart, and it will tell you right away. And then, of course, then what's left, dv has to be just dx, which is the only thing that's left. And then the whole thing comes out nicely. And the bottom part, the only thing is, you do some quick substitution, where you know that the second integral right here, the second integral is just the natural log. Well, you have to divide by 2 in order to adjust for the constant. We're doing the differentiation, and that's the right answer. Okay, so let's look at problem 11. Same thing. Problem 11, we're again following the rule of Liat, which says that the algebraic expression which is x in this case, should take precedence over the sign, which is the trigonometric. So we'll let u equal to x, v equal, then dv is just whatever's left, and then you can follow the formula, and the result pops right out, and that's correct. And then, so that's problem 11, and problem 13 is basically the same way. Not much happening in problem 13, where again you let u equal to x, then and then let dv be the rest of it, because e in the Liat rule comes to the end. See, so then so dv becomes the rest of it, because e is very easy to differentiate or integrate, and as long as you pay attention to all the negative signs that might be involved, and then you do the integration, and the answer comes right out. Okay, now next let's look at problem number 15. Where is it? Right here. Again, the problem 15 is also very straightforward. The trick is simply choosing u equal to x squared, following the Liat rule, where x squared is the a algebraic expression, and then dv is just the rest of it. And so you do differentiation, integration, and everything comes out nice and neat. So that's, I think, right? No, actually in this case you have to do it twice. Okay, the actual answer you have to do one time, and then you end up with a sign, and then you do it again, and then end up with something. The second time, then you end up with, no, I got rid of the integral sign entirely, which is fine. It's slightly longer, not by a lot. Okay. Anyway. So next problem. The next problem is problem 19. Problem 19 is similar to one of your examples, where you the thing repeats itself. Okay, that is, if you do the integral, then the first time around you end up with something that's very similar to ex sine x, and then you end up with ex cosine x. How's that different? Well, what happens is if you crank it one more time, you end up with ex sine x again, in such a way that you can round it up to have 2 of them, and then your answer will fall out. So you have to do it 2 times, which is still not too tedious. Let's see. Next, let's look at example 23. All right, 23 is a similar situation, I think. In fact, it might even be identical to example 3.5, which you have already done. But the point is, you follow the rules, okay? You let u equal the sine of natural log of x. Yeah, it's almost identical. And then when you do it again, you see the same thing show up again, which you can put it all on one side, and then you have 2 of them. And when you divide by 2, then you get the right answer. All right. And then what's this? Example. Then next, let's look at problem 25, where u is the natural, the integral of natural log of x squared. That is, so now what? You just let u equal the natural log of x squared, and then by the time you calculate the du and stuff, it falls out nicely. Okay, even shorter than the previous problem. Yeah, so that's that. So there's not much to say there. Next, let's look at problem 26. Problem 26 is very similar to problem 25 in appearance, but they don't work the same. And then where the location of x is slightly different, but that creates a different problem. However, it works out nicely anyway. Okay, as you can see, if you let u equal the natural log of x squared, everything just falls out in one step, actually. All right. So next, problem number 27. Yeah, that also looks like pretty straightforward. You let u equal the natural log of x, following the Liat rule, right? The natural log comes first, and then you do du, and a couple steps later, here's your answer. Nice and clean. So the next we have problem number 35. Next, problem number 35, where you have to deal with the inverse secant. Now, according to the Liat rule, the inverse secant belongs to the I, okay, inverse trigonometric. So it will be a chosen option for u. So we will have u equals to secant inverse of x. And then what is the derivative of secant inverse? You might not remember it. That's fine. Just go look it up. And somewhere in some chart, it'll tell you that du is equal to that thing. And then you continue to follow. Now, there is an absolute value there, so you have to be somewhat careful. How do you integrate something with absolute value? The only difference is that you have to watch out for the negative sign, like what happens if x is negative. And the way the book presented the answer is you just take the square root of x squared, okay, and then that takes care of itself. But at first, you can just pretend the absolute value doesn't exist and come up with the answer first, and then you can take care of the details such as the absolute value. So that's that. And then the next problem number 47, which is a short and sweet one. We have the natural cosine of x and natural log of sine of x. Well, you do that by let u equal the natural log of sine of x, and so on, and then everything falls out right away because things cancel out nicely. So you just have a short and sweet answer after one line. Okay, so that's good. Next, we have next page. Okay, problem number 49. Problem number 49 doesn't want you to know the answer. It just wants to know the formula, which is even shorter yet, so you don't have to do the integration. So you 49, following the Liat rule, you allow u to be x to the power n, because x to the power n is the algebraic expression which comes before trigonometric, and cosine is trigonometric. So once you let x equal the power x to the power n, and you follow the formula, and then out pops the answer, and you don't have to integrate anymore because that's all the book wants, just some kind of a formula for doing this type of thing. And then all right, so next let's do problem 53. Problem 53 is a review of the substitution method of integration that you learned back in calculus 1. The substitution method, of course, goes very, very quickly. So when you look at like problem 53, okay, you're looking at the integral of natural log of x squared over x. Well, the natural log of x differentiates into 1 over x. So that's all taken care of. So all you have to do is just apply the power rule. So it becomes natural log of x to the power 3 divided by 3. And yeah, and then that's about it. Because if you take the derivative of that, that will become the integrand of the other side. Or you can do it slightly longer and let u this is u is for u in substitution. U equal the natural log of x, du is 1 over x dx, and etc. Okay, and that will come out with the same answer. Now, if you don't remember how to do use substitution, which is the integration by the chain rule, please look up the part in chapter 1, which explains how to do it in detail, as well as give examples that you can practice. A couple of practices should bring you right up to speed. Next, problem 55. Again, same thing. You don't need to do integration by parts with that problem. You just use the good old integration by the integration by the chain rule. Okay, you just reverse the chain rule and the answer pops right out. You can actually stare at it and write down the answer in your head. And similarly, the problem number 57, same thing. Okay, just stare at it until you figure out what function, if you apply the chain rule, would come up with after you differentiate it, will come up with the integrand in the integration. So you come up with that thing, and then that's about it. And then adjust the numbers. Okay, like 57, I think you have to divide by 9 because there will be a 9 after the differentiation, which is not in the result. So you have to divide it out, and then everything will come out nicely. So that's that. That's number 57. Next, number 63. Problem number 63. Well, I'm not going to talk about problem 63 until the next section, because as it turns out, as I mentioned in the notes, problem 63 is actually an example in the next section. So we'll talk about it when that happens. All right. And the trick is that, number one, to do problem 63, you have to let u equal to secant x, and then you have to plug in the trigonometric identity that says tangent squared plus 1 equals secant squared. And once you plug that in, things should fall out pretty nicely. But we're still going to do it in the next section, being that we're going to talk about it anyway, right? So we'll wait for it then. And let's move on to problem 65, where you're supposed to integrate this thing, but except that you're supposed to evaluate it, which is fine. It's a fairly simple problem that you have already done probably, or something similar. So you just let u equal to x, and then everything will fall out, except that now you have to evaluate it, which is still okay. You just evaluate it either in your head, okay, remembering how sine and cosine works, or plug it in some calculator. Either way, that will pop out with a nice answer. And that's the end of our problems. Now the problem, as you can see, the integration by parts, for the most part, is kind of a neat little trick to handle certain kinds of problems that we don't know how to integrate otherwise. But as always, remember that integration works in such a way that no matter how many tricks we come up, there's always another integration problem that we don't have a trick for. Okay, so because of that, we will continue to learn more tricks to hope to be able to do as many integration problems as possible.